Who doesn't know this Sesame Street creature? Pretty much everyone knows him. This is the Count. I looked it up. Actual name is Count von Count, and my talk today is about counting. So we're going to start off with a little counting game, and I think everyone knows what to say, but I want you to count along with me. It's not going to be that difficult. Ready? 1, 2, 3. You can count with me. So very good, very good. Now it's pretty easy counting, but this is an experienced audience, and we have a lot of observability monitoring practitioners here with years of experience. So we're going to try another count along, and this one's going to be a little bit more challenging. But I want everyone to do their best on this, because you all know once you see it, you'll know it. And let's go. 256, 65,536, 2,147,483,648. Who knows what comes next? Some of you know, if you've been in an incident, you may have been on call and fielded an incident that comes up with this number. Any guesses? No? -1. So welcome to my talk, Use Counters to Count Things. There's some links here. You can find me on social media. I've got a Twitter account, but I don't really use it that much anymore. So hi, I'm Fred. I work as the principal engineer at Zendesk. These opinions in the talk are my own. I've been doing the observability thing for a while. I like to do time series databases. I made up a special type of histogram for Zendesk. Been writing programming languages for a long time. And I'm a dad, so I've got 2 kids and 1 puppy. And so I really appreciate the pour over out there. So let's get back to counting. I'm going to start off with a story. And this was a long time ago, 2007. What was that, 17 years? In a company far, far away. And it was New Year's Eve, and I was getting ready to head out to meet a couple friends to celebrate the New Year. We're on the West Coast, so the ball drop in New York City wasn't a feature there, but this is the actual ball that they used in New York City, I think 2004 to 2007. It looks a lot different when it's not lit up and up close. So I was going to head out the door, and my phone rang, and I didn't recognize the number. Did I mention I was on call? It's like, hey, Fred, it's Sean from the NOC. And that NOC stands for Network Operations Center for Cloud Native folks. And I knew right away that Sean was not calling me to wish Happy New Year's Eve. And he told me, hey, all the systems are down. It's called the block system that we use to process email messages. And part of me thought, like, okay, we've hit some sort of end of year bug. Maybe it's a little bit early. And this might be kind of fun to solve, because I've never solved like a New Year's Eve type of bug. But I knew at that point my plans for the night were on hold. So grabbed my laptop, logged in, started poking around. And this was 2007, so the observability back then was fairly limited. We were using Nagios, however you pronounce it. All the system, all the hosts seem fine, functioning normally from a resource standpoint, but the request rate was close to 0. And so I started SSHing into production servers. We used physical servers back then, and checking to make sure, like, okay, Apache's up and it's running fine, and just kept looking around. And as midnight passed, I was about 30 minutes into this, and I kind of took a step back and tried to gather myself and look at it and think, okay, what could it be that's going wrong here? And this system, it would we had a bunch of honeypots out in the wild that would try to grab spam messages, and it would pull these incoming messages, and try to group them into batches. And then we had a group of folks who would, some of these, it would automatically classify as spam, but we also had users whose job it was to look at these groupings and say, like, yeah, this is definitely spam or not spam. And the web interface that they were using was throwing that dreaded internal server error each time a user tried to access it. And so I looked through the Apache error logs, and I couldn't find anything really except for a bunch of generic 500s coming in. There was no stack traces, nothing. So I started digging around the code. As I mentioned, there's no distributed tracing, or that would have been extremely helpful. So I did what any good software engineer would do in that situation. I took one production instance, opened up VI, and started dropping print statements through the entire code base. And within about 30 minutes, I was able to find the subroutine that was causing what ended up to be an unhandled exception. So that would bubble all the way up to Apache's error log handler, and it would just say 500. I don't have any more information. And at that point, I knew exactly what the problem was. So looking at this is the line I found. Who has an idea what this problem is? So as we brought these incoming email messages in, they would go into a MySQL database, which would use a serial, which is basically a counter, to provide the message ID. And so when the web interface would grab the message out of the database and grab that ID and pass it through this printf statement. And it turns out that night we had just processed our 2,147th million and change message, which resulted in the message IDs going negative since it used %d signed int interpolation. And so numbers started going negative, which the rest of the code base couldn't handle. Did I mention that this was a code base written in Perl? Ancient language. Shout out there, Brad, who's still using it. So Perl happily took that ID, cranked out a negative message ID, which caused unhandled exception and caused the whole thing to 500. So quickly, I swapped out the %d with a %s, not float. I restarted Apache, and voila, the spot instance started working again. 30 minutes later, and I had the whole thing back up. But at this point, it was close to 1:30 a.m., and my New Year's Eve had come and gone. However, I did get to add to my quiver. I handled an int32 rollover as an SRE, so that was nice to get. I didn't get a merit badge, but got a nice pat on the back on Monday. So how many folks here, show of hands, have you fixed something like this in production? Wow, a few, okay. So you're all experienced here, and we all know about this issue. And so we know about it because so many of us have been bitten by it, and these stories have made it out to conferences like this. And we know now that we should use 64-bit ints on anything that might find itself hitting this limit one day. And we can relish in the knowledge that we're part of an advanced group of practitioners that have learned from history and helping out the industry, and no one should make this mistake ever again, right? Well, last week I saw this. I'd like to express my thanks to GitHub for surfacing this piece of content for my talk. Apparently, they had used an int32 in their issued common IDs, and it caused Rust-Lang's RFC bot to fail. So it turns out history does repeat itself. Did I mention this talk was how you should use counters to count things? Well, I didn't say there weren't gotchas. But let's take a look at another story which demonstrates a way to count things. Story number 2, more recent, and I have to classify the date on this one just because it had to do with a security incident, and so I had to redact a bunch of things. But it involves another method. And so one day I get pulled into a secret chat room, and our CISO says, hey, I need some help. And he said, I can't tell you exactly what happened and what prompted this. And I told him, like, you know what, that's great. I don't want to know. You keep that to yourself in whatever other chat room you're working the main issue in. and they said, we need to figure out how many times a certain thing had happened in our web service over the last N amount of days. And so I started digging, at this point, it was recent enough, we had metrics, traces, logs, all that stuff. And so I started digging into our metrics because I figured I can find a counter that will just, give me this number. And I was able to find one, but it didn't have the dimensions or tags which would break it down by what I needed. And so while I said use counter, sometimes one may find themselves in a position where that's not an option, or you might not have the necessary metadata on those metrics. And the only place I could get this information was our logs, and so I let them know I'd have to run an exhaustive log search. He said, great, you can have it by the end of the day, right? And that's where things got a little complicated. So over the time range that I was looking at, it was a double-digit number of petabytes to search, kind of on the order of what you may have seen on some of the other vendor and larger talk presentations. And in the past, I'd used AWS Athena to do these large-scale searches, but the cost was about $5 per terabyte. And so I was looking at running a SQL query in Athena that would have cost on the order of one engineering headcount for a year. And I kind of broke that to him gently and said, well, go figure it out, basically. And so I reached out to an engineer on our machine learning team, and we decided to try and solve this with an elastic MapReduce EMR cluster and some AWS SageMaker code. SageMaker is similar to Apache Spark, but it has some different libraries. You can write processing code in Java, Scala, Python, and you can bring to bear most of the libraries out there for the language. So we deployed, I think, a few EMR clusters to parallelize this operation, put together a SageMaker program, and fired it off on a test run. And that approach worked, so we figured we could parallelize it and be done in a couple of days. But unfortunately, what we found is when trying to process this much log data, the EMR jobs would randomly die on us. So I had to sit there and babysit a lot of these jobs. They would die. I'd figure out how far it had gotten, figure out the offset in the logs, and fire off another job. And that went on for about 2 weeks. And I know what you're thinking now. Why didn't you just use ToolX or one of the vendors out there in the hallway? So the devil's in the details. We didn't have any of that available. And when you're trying to get something for the the chief information security officer in a bind, you have to do what you need to deliver as quickly as possible, even if it means employing some duct tape and restarting jobs. So we were able to deliver the counts along with the breakdown of dimensions needed. It ended up being a lot less costly than Athena, but still it was considerably more than a quote high cardinality metric would have cost. And I call this counting things the hard way. I think it was Dave Josephson's talk yesterday had a good reflection on this approach, where once the data gets into storage, queries are much more expensive than if you could have refined that data early in the pipeline and perhaps created a task-specific counter for something like this. And he was spot on for that observation. And out of it, we had one happy CISO, which made the effort worth it. So let's get a quick look at the lessons learned from counting things using counters versus log scans. Like most things, counting things using a counter-based or scan-based approach is a set of trade-offs. So counters are cheap. I can store the results of the equivalent of petabytes of logs in 4 or 8 bytes. That's a no-brainer. I went to lunch with a few colleagues a couple weeks ago, and they said they were waiting for part of our data warehouse to be stood up to get product telemetry running for a certain part of our service. They were going to, shove all the logs in there and then run batch jobs over it. And I told them, listen, you're going to be waiting a while. It's extremely expensive. Drop a counter in, add the tags or dimensions that you need, and you can buy me dessert with the difference. And they were concerned about that. I call it the specter of high cardinality, but honestly, I don't really believe in that. Metrics are awesome as long as they are scoped smartly. You can make just as many mistakes with logs or traces and explode your telemetry volume. The other nice thing about counters, they're commutative and associative. You can fetch those from many nodes and add them together, the order independent. They don't suffer from lossy aggregation like gauges do with averages or any of the well-known percentage aggregation non-math that I've ranted about previously. And there's a good chance that you already have instrumentation up and running for this. But on the other hand, counters are expensive. That 4-byte int32 could cost your company hundreds of thousands of dollars in downtime. Getting the correct instrumentation, manual instrumentation for the business can take a lot of work. It's not like a catch-all with logs where there's a good chance someone already has dumped the piece of information you need into logs and you can sort through it later. It takes some planning to exploit their cost effectiveness. And then there's the cost of not doing your tagging smartly. Generally, that's not a problem, but we've all been there when either a framework or an engineer decides to drop an account ID, an IP address, or a request ID as a tag into a request counter, and your metrics, time series explodes with high cardinality. But when you engineer it correctly, you can use counter metrics on such things as like account ID to measure the same thing by scanning logs or trace spans, but you can do it with much greater efficiency and cost. Let's talk about log scans. They're cheap. You can do those out of band and they're done ad hoc, so it could be you're logging a bunch of things and you never even need to look at it. New attributes can be dropped on without exploding the number of time series you have. And printing to standard out or standard error is really easy, as we all know engineers like to do. And that's all you really need to get going. But, I've come to the conclusion PB stands for pain in the bite. Scanning petabytes of logs is expensive and painful no matter what tooling you have. What about indexing you might bring up? Like the Netflix talk the other day mentioned, you can create different types of indexes for different types of searches as long as you know what searches you need to do. But though at that point, are you essentially making a time series metric? In some cases, maybe. Has anyone here run a query that could cost like $10,000? It's unnerving. You hit go and you're sitting there waiting, and if it fails, your company is out a bunch of money. So I know some folks may get after me about pitching their product for that, but what I'm talking about here is really bespoke counts for customer security needs. If you don't need a particular query every day, the operational cost of it may be more than you think. And a lot of standing up like a data lake or data warehouse, a lot of that cost per query is masked behind just keeping the thing up and running and a lot of developer time. And finally, one thing I've learned is logs are subject to delivery issues. Abstraction layers like Kubernetes can rotate logs out of the file system in bursty workloads, and your log aggregation tooling doesn't have a chance to grab those logs. Common thing I've heard from folks is like, we sent these logs, but they're not showing up. Well, when you're dealing with that many, you're not going to get petabytes of logs. You're going to lose some. And if folks have ever run in what observability tooling you have, your log search, you'll run a search and you'll see it just spin there, trying to get a count. That's one of the challenges I'll talk about in a couple slides of counting large numbers of things. But you can keep a count of how many logs you send, and you can do a scan, and those won't always match up. And at high traffic, at high scale, there's almost always a difference. Which answer is right? I think the answer is generally, it depends. So I mentioned we're going to talk about counting large numbers of things. There's this count distinct problem that folks are more than likely familiar with. And this is counting a distinct number of things is a different problem, and it's a tough one in computer science than just counting a total number of things. So we'll take a quick walk through some of these solutions. This could be a problem you face saying like how many distinct users visited the site yesterday, how many distinct users liked the social media post. At scale, it's a problem that you'll either need to find tooling which can solve it or implement one of these algorithms I'm about to show. So we're off story time for computer science. So there's the, to try and count the number of distinct elements in a set, there's the quote naive solution. And folks have probably been asked to solve this problem in a technical interview. This approach is relatively straightforward. You have a hash, you add a key to it and bump a count every time a certain element is seen. And then you can take the count of distinct number of keys, and that's the number of distinct elements in the hash. And as a bonus, you get the breakdown of counts by key. The trade-off with this approach is that you're bounded by the available memory to fit all those keys in. So this is something that is not going to scale terribly far. It'll go ways, but for something that's really large, we need to take a different approach. How many folks have heard of hyperloglog? A few. This has stuck in my mind because I had that exact interview question one time. I gave them that naive solution, and then I actually didn't know about hyperloglog at the time, and it educated me, and I have never forgotten that since. You get a question wrong in an interview, and for a lot of us, you're never going to forget it. So hyperloglog is an approximation algorithm which assumes that your data set has a uniform random distribution. That may not always be the case. So there may be a couple folks here who have implemented it, so thanks for your understanding on this next slide, where I try to explain the algorithm in 3 lines. How does it work? This is an abbreviated notation I put together. So each element in the set is hashed. We'll call each element I. You convert it to a binary representation, so a bunch of 0, 0, 1, 0, 1, whatever. And then over that entire set, you compute the maximum number of leading zeros as n, and your estimate of cardinality, total number of distinct elements in the set, is to the nth. Now, this simple estimate, it does have a large variance, and in actual implementation, one would process multiple subsets to get a more complete estimate. I can't do the justice to this in one slide, so I'd say go read either the paper or a more detailed explanation. And one, I messed up. Oh yeah, it's reasonably accurate, within 2%, and memory space takes in the kilobytes, so it's fairly efficient. I mean, I'm guessing, some of the very large companies, Google, are using some variation on this to do counts of, unique users or Facebook likes or something like that. So May 2023, last year, a paper was published by 3 authors, and the algorithm was named after them, the CVM algorithm, and this is an approximation algorithm called disjunctive normal form. There's a link to the paper right there and a sample implementation in GitHub. And supposedly Donald Knuth contributed to this as well. I learned about this on Hacker News, as some of you probably learned about it also. But I really wanted to dive into it for this talk about counting things. So how does it work? I abbreviated out how it works here. I came across a reasonably readable explanation in Quantum Magazine where it talked about counting the number of words in Shakespeare's Hamlet, which is about 4,000 words. The short version is this. You set a fixed number of hash keys corresponding to how much memory you can allocate. For example, I could declare a hash with 1,000 key spaces. You want to start reading through the set, in this case, words from Hamlet, and stop when you've read 100 entries. And once you've filled up that hash with 100 entries, you walk through each key and you make a coin toss decision, 50% keep, 50% delete, and you delete, at random 50% of the keys, leaving one with, in this case, 0 to 99 entries, but more likely right around the median of 50. And then you walk through, then you read the next amount of words corresponding to how many free slots you have in the hash. But on the second iteration, you walk through all of the hash keys, and this time you do a double coin toss, since this is the second iteration through. You go through it a third time, and you do 3 coin tosses for each element. And when you've reached the end of your set, you will have n keys left in your hash. You divide that by 1 over 2 to the number of rounds. That's your distinct number of elements. This is somewhat easier to implement practically than hyperloglog, and it's shown to have higher accuracy than the 2% with hyperloglog. And plus, this is something that once you get in your head, you may be able to pull this off in a whiteboard interview next time you apply for a job. So, take this one and run with it and amaze your interviewer that you know something really cool. So that's a wrap about counting. Thank you.
All right. Are there any questions? Hold on, I gotta get out of this light. I can't see anything.
No questions about counting or Sesame Street? Any Sesame Street questions? All right. You're dragging. I know you had the sugar. Is this the sugar drop after the 300 donuts or however many we had? 400 donuts. 400. So, great. All right. Let's give a big round of applause to Fred.
Thank you.
Thank you so much.